I will be introducing what indexes are used for and the motivation and some important aspect that you need to be aware of. And then we dive into two ways to create indexes, or two major ways. This area is an active area of development. Always there are new ways of building indexes. So, but by far the most widely used techniques are tree-based indexes, particularly B+Tree index and hash index. So because this lecture starts to become too long, so I divided this into another set of slides. Okay, so let's first introduce what an index is. Any idea what's an index and what is it used for?
Something to speed up the lookup process.
Okay, so that's the role. The role of the index is to speed up retrieving or speed up reading data from disk. To be able to answer the queries very fast, to speed up the query execution. Any other? What is it at the end of the day? Hash table is one implementation. Yes.
It's the way that you reach the data, the pointer.
If we don't have an index, what's an alternative? How we can get to Yes, that's the ideal. So I gave you before the analogy. If you have a book, for example, I ask you to search for pages that discuss or talk about or refer to B+Tree. One way, or you will go through page by page and look carefully if that page mentions B+Tree. And then you will give me the page numbers where this topic or this concept is discussed. So in that case, you will do full scan of the book. What's the problem with this approach? It's time consuming. It is very slow. So what could be a better way if I just ask you what pages in this book discuss or explain or talk about B+Tree index?
Look for index.
Go to the index at the end of the book, and then what you will find in the index in there. What is an index? So the topic, which is the key, the key we'll use to search, and then what is associated with the topic? The page numbers. Yeah. So the index in database is exactly the same. So you have some keys, and these keys have what associated with them?
Index.
Sorry?
Index.
No, the index is made up of a key and page numbers. Thank you very much. It's pointer to page numbers. Remember, the files, the way they are organized on disk are divided into pages. So let's say we create an index on the student's ID. We have a student table, and we create an index on the student ID. So the index will have all the students' IDs, because that's what we will be searching based on. And associated with each student's ID, what we will find? The page, the disk page on which that particular ID happens to be. That's exactly the same idea as the index at the end of the page, of the book. And the role of it is to speed up data access. Okay, so far we have seen the disk manager as one of the components of the database. On top of it, we have the buffer pool that allows us to basically cache the pages that we load into memory. And on top of that, we have access methods. These are nothing but indexing structures that allows us to speed up reading and writing. So when we talk about indexing, we basically talk about two things. We first talk about the data structures that we use. The data structures. The main structure is either tree or hash table. Plus, of course, when we talk about data structures, we will talk about the algorithms to read and write to those data structures. So that when we study the topic of indexes, that's what we need to study. We study the typical data structures used to create an index and the algorithms associated with these data structures to basically add entries to the index, looking up, searching through the index. That's what this topic really entails. So before we dive into this, into indexing, we need to first be aware of different query types. So when the typical queries we run against our database, it can be categorized in many types. And the reason why we need to be aware of these types is that some indexes are more suitable for particular types. So when you study this topic of indexing, you will find, for example, B+Tree index is more suitable for range queries. You need to know what range query is. Or somebody will tell you the hash index works only for point queries. It does not work at all for range queries. So you need to be aware what a range query is. Okay, so it's very simple. So first of all, point query, you can see it here. This is an example of a point query. So it's...
Typical index, when you create the role, what's the role actually?
The role?
Of who creates the index, the number of the DBA.
I see, the role who creates this index. So there are two roles that get involved in this. Usually the developers, they create the index if they have the luxuries to do so. Otherwise, they make a request. During development, of course, they have that luxury to create the indexes, and they give all the scripts to the DBA to run to create the database, including the schema and the indexes. But in the future, as the application grows and so on, you might start to see some queries are poorly performing, and to boost their performance, you might need to create some more indexes. So you will recommend such indexes, you test them, you create scripts, and then you go and beg that administrators to run them. In reality, that's how it works. Database is very important piece of components in an enterprise. So it is highly controlled, especially developers. Developers are the last people to come near the database. So to cut it short, developers design them and even create scripts for them, but the DBAs really create at the end of the day. Yeah. They are also, of course, responsible of tuning the database to make sure that it runs to its best performance. When I say tuning, for example, as I explained before, reorganizing the tables, reorganizing the data files. There are commands that they should be scheduled on a regular basis to do this. So if the database performance start degrade, we should look at those jobs, scheduled jobs. Are they running? Is there any issues? Are there any issues? So it's a collaboration between the two. But for you to make the right decision, which indexes to create, you need to be aware of the queries that you as developer, you are writing against that particular database. The DBA will not have that visibility of the inner working of your application and queries you are running. Yeah. Okay, point queries. And when things go very bad, you have to hire some company specialized. They go investigate and help you solve the problem. That's the reality in the ground. There are companies, that's their job. It's basically specialized on fine-tuning databases to boost their performance. I've seen this in the real world. Yes. Okay. So point queries. You can see here there is an example of a point query. It is typically in the where clause, you are looking for particular specific data, usually based on some kind of key, and you are using equality in your where clause. Yeah, that's basically what's a point query. It's not necessarily on the primary key. On any key, you are searching for something, typically using equality. That is called a point query. Now, as opposed to a range query. In a range query, you are looking for some data based on some key where the value is in a range between two values, between a lower bound and an upper bound. This is called a range query. Another type of query, sorry, there is a distinction. Maybe I wasn't saying it accurately. So point query, it is expecting one result. You are looking the data by primary key. So in here, for example, the number in this case here is a primary key. So the returned result is one record. In here, multi-point query, when you are querying using equality, but you are querying on a non-key, which means the results could have multiple records coming back. Such as in this case, you are getting all the accounts where the branch is, let's say, QU branch, for example. So the other type of query is called ordering query. Ordering query, where you have some order by clause. You are not only getting the records, you are getting them in particular order. There's another type of query is called prefix match query, where you are using something wildcard. You're saying, give me all the employees where the name starts with J. Yeah. Here the syntax differs. In SQL Server, we use a percentage. I'm not sure star, maybe some other database use this syntax. But the point is, in here, this is special type of queries. And by the way, this is where research and development goes into. We have this major type of indexes. And then there are some special types that are more optimized for particular types of queries. So some people specialized on just on this type of queries, trying to come up with some better ways of answering that particular type of queries. Yeah. So what I mean here, be aware of this, because as we go forward, we might be mentioning this type of queries moving forward. Another type is, this is a scan query. This type of queries, index will most likely will not help you much, because you have to go through the whole table to answer this. This is called scanned query. Extremal query. So even if you type this one in Google, you will find some research papers just focusing on extremal queries. What these extremal queries have, like you have here a subquery. For example, here you're getting the maximum balance. And then you use that result to get the accounts that has the maximum balance. So it's a kind of two queries. Subquery gets executed first, and the result is used in the main query. Group by queries, here this is some kind of aggregation. I'm grouping here by grouping accounts by branch, and then getting the average balance per branch. And finally, join queries. Here, most of the queries I showed you before are looking at single table. In here, I am joining multiple tables. In this case, joining accounts and branch on the branch number, and adding this where clause. This is called the join query. Just be aware of these different types of queries. That as we move forward, we might mention them, so at least you can picture them in your mind. Okay. So here is the definition of an index. So an index is a data structure that supports efficient access to data. So instead of going directly to your data file and start fetching your pages to look through, to scan them and look for to look for records that meet your query. Instead, you go through the index, and the index will guide you to which data pages you should retrieve. Instead of doing the full scan, you selectively just retrieve a couple of them to answer the query. Yeah. So it's basically another layer between you and between your query and your data file. So you don't go directly to the data file, you go through the index, and the index will tell you, will point you which data file or which data pages you should fetch and to look for answers to your query. That's basically the role of the index. And it is exactly the same as I explained the index in the book. So you go through the index at the back of the book, and basically what you have there is you have the keywords and you have pointers. In this case, the page numbers that you need to go to get more details about that particular topic. Okay. So they help us to avoid full table scan. That's the idea. They help us to avoid full table scan. And we can, when we define an index in terms of relational database, when we define an index, we define index on columns. So you remember, table is made up of columns, and we go ahead and we can create an index based on one or multiple columns. And the index at the end of the day, the index will be a value of the key and the associated pointer to a data page or to a page on the disk. So it's a pair, which is the key, key values. Key values, for example, if you are defining an index on students IDs will be your key values, and your pointer will be the page IDs that have that particular, for example, that particular student. So for each value of the key, you will have an associated pointer to guide you. So if you are looking for students 1, 2, 3, you go through the index, and the index will tell you students 1, 2, 3 is in page 55. And you just go to page 55. In this case, you do two lookups, one lookup on the index and one page fetch, one data file, one fetch of the data page, one fetch of the data page, because the index will tell you exactly which page you need to fetch to answer that particular query.
So that will give you the page, not the record indication.
We will see. This is just in general, but there are different types of indexes, and each type will give you different things. But remember, at the end of the day, if it just gives us the page, this is super good already. Because remember, what is the basic unit of reading and writing to database? Is the page. Yeah? So even if your records happens to be in the middle or wherever in that particular page, there is no way. You have to bring the whole page into memory, and you have to scan it again, or somehow, if you already know, remember the page has slots, if you recall. We have an array that has the slots with the record IDs associated with the offset on the actual page. So the page has a slot array, and they have the actual data. So once you load the page, then if you have the record ID, you can simply jump to the offset and read that particular record. Yeah? So if we go to the page, we already got to our record, because we get the page. The most expensive part of the whole operation is getting the page to memory. Once we get the page to memory, the rest is insignificant compared to fetching it from disk. So the index tries to help us reduce the number of fetch that we need to do from disk to the buffer pool. Okay, and this is just a visualization of what I just mentioned. Now, the indexes are so good, they help us to get to our data very fast. Does that mean we just go ahead and create an index for every column on our database or every column of our tables? Is that a good idea? In what way worse?
It's like a copy, so it will take also storage.
Yeah, so one cost is the cost of storing the actual index. Yeah. You might say, okay, the disk, who cares about the disk? It's very cheap and abundantly available. But you'll be surprised, it's not the cost. Sometimes the cost of backing up and restoring. You don't want your database to become too big to make it very hard to back up and restore. Yeah, that's very important. Remember, like every night that DBA will be shooted at if the backup fails or backup didn't finish by the time people come to their work. The backup should finish at night before people come. So you don't want to overdo it and then you have a huge database just because you have so many indexes. But that's not the main reason. It is a reason, but not the main reason. What is the main reason why we should not just blindly go and create indexes on almost every column?
Small tables. Small tables.
Small tables, as you mentioned, is not a problem. You can scan them, and maybe the small table is in one page.
Because I will also take time on the indexes to reach to search on the index itself.
This is
No,
for the
not
column
really.
that not
Not really. Depend on the structure of the index. We will see. Yeah.
the column that they don't have a duplicate value. It is and mostly unique. This will make a problem if we.
No, not really. Like depending on which indexing strategy, which indexing algorithm you are using.
Maybe it doesn't help every single query, like scan queries are not the
Yeah, I know, but I don't want to spend time thinking too much. I just create indexes on all columns, hoping some queries will take advantage of them. But I cannot do that because there is a trade-off. First is the speed. First is the storage. It takes this index will take some storage space, and more importantly, when the data change in the underlying table, what happened to the index? You have to reflect the changes in the index. That's the problem. Imagine you are writing a book, yes? And then you create an index. You're supposed to create an index towards the end when everything is stable and you're almost going to print. So if you create the index early, guess what? As you change things, you add more content, the pages get shuffled around. What happened to your index? Out of sync, useless. You can just throw it away. Yeah? So the problem here, when you have indexes, when you insert something in your data file, what you should do? Update the index. That is the problem. If you update something in your data file, you sync with the index. The more indexes you have, basically your writes, your inserts, updates, and deletes will take longer. Yeah? So there is a trade-off. Trade-off between what and what?
How big the index?
How big is okay? Like, yes, we know that. Like the index, that's not the main. It is one of the aspects that we need to consider when we decide which indexes to create. So we need to be mindful that those indexes that we create will take some space in this. That's one thing. The other trade-off we need to be aware that there is a computational cost to maintain those indexes in sync with the data files. So we only create the indexes when we believe that there is the performance gain we will get from these indexes outweighs the cost to maintain them. Yeah. So we cannot just blindly go and put indexes on most columns or all columns. We have to be very careful in selecting such columns. So what do you think? How do you select such columns to go, the lucky columns that will have the index?
Primary keys of large tables.
Primary keys? Primary keys by default they get an index. Although, yeah, primary keys they get an index. Why do you think primary keys by default get an index?
Because they are for locating a certain column.
Because very often we do lookups or we do queries, at least point queries, using the primary key. For example, in a student table, we have the student ID as the primary key. So when you go to registration or you go to any of the, let's say registration, the first thing they will ask you, what is your student ID? And they will type it in to look up your record. Yeah. So basically, the columns that we use heavily in the where clause, remember the where clause in the queries, the ones we use heavily in the where clause, the ones we use heavily in joining tables, yeah, The ones we use for order by, the ones we use for group by, those are good candidate columns to put indexes on, because they will speed up our queries. The columns that we very rare we might put some query where we use that column in the workflows, those you never put an index on. Or you can, if you want to put an index, temporal index, do those queries and drop it. It's fine. But don't put a permanent index in there. For example, in some of your designs, I have seen some of you add some kind of record and say added by, added on. This is very common in those of you coming from practical systems. Enterprises, they always want to know who did what and when. So whenever somebody does anything, we store it in the actual table. But we should not put those columns added by and added on. We should not put an index on them. Very rare we will look up those, except when there are some auditors. But auditors, again, anyway, this practical stuff. Auditors, when they come, they can bring your database down because they run some funny queries. So usually what we do in real life, we take a copy of the live database, we back it up, and we store it in some server, and we say, here it is, enjoy, and every day we'll give you a fresh copy. Otherwise, they will bring down your database. Yeah? Because they try to do some funny queries. They say, give me the transactions created after 5 p.m. and from 5 p.m. to 7 a.m. They want to see if some transactions created outside the working hours. Sometimes they want to say, oh, there are transactions. Give me if there is some gap between these transaction IDs. I want to see if somebody created a transaction and deleted it to remove some trades. You know, those people have their own mind, so we will not design our database for them. So what I mean here, you carefully select the columns to put the index on, based on what, as I said? To frequently used in workflows, in join, order by, group by, and so on. These are the main ones that you put. Yeah. So please keep this in mind. So there is a trade-off between the computational gain of using an index and the computational cost of maintaining this index. Whenever we do an insert, update, delete, we have to do it in two places. We have to do it in the data file, and we have to do it in all the indexes created for that table. Very important. Otherwise, the index will become useless. Of course, there is the extra space. What I also say that, remember, the indexes are also stored in disk, and they will slow down our insert, update, and delete. So we don't want to favor, if we put too many indexes, we might favor the queries, the reads. But who will pay the cost? The rights queries will pay the cost. So we want to keep it balanced by carefully selecting. Now, in terms of extra disk space, yes, there is extra disk space. In terms of cost of that disk space, it's becoming more and more insignificant. But as I mentioned, keep in mind, this is a practical thing. The bigger your database, the longer it takes to back up, the longer it takes to restore. If something goes wrong and your backup is very big, it takes very long to restore it. But if you keep it slim and nice, it's much faster to back up and restore. So only create the index when performance gain from having that index outweighs the cost of maintaining it. Okay. Moving on, another very important concept came to me in one of the job interviews is clustered index versus unclustered index. Very important to understand. It will, in this world of, if you are working any practical, as an application developer or as database administrator, definitely you need to understand this. Very important concept. So there is clustered index and there is unclustered index. Anybody have an idea what's the difference? Okay, so clustered index, here is the index. So basically the data, the data file and the index file are one thing. If they are stored as one data structure, that is a clustered index. And also the data is sorted based on the clustered index key. So for example, if you have clustered index on the student's ID, so the data of the student records will be physically sorted based on what?
Student ID.
The student's ID, based on that clustered index. So the sorting of the data is based on the clustered index. And not only this, the data and the index are one thing, are one structure. Yeah? So for example, if you are using a B-tree, which we will discuss later, in the leaves of the tree, you will find your data, the leaves in the tree. In a non-clustered index, if you are using a tree, in the leaves of the tree, what you will find? The actual data? No, you will find pointers to the data. Are you following? So what I mean here, in the index, clustered index, the data is actually stored with the index. And the data is sorted based on the index key. Yes? How many clustered index you can have on a table? One. It makes sense, yes? Because the data is sorted based on that key. So you cannot have multiple clustered indexes. So you have one shot. Of course, you better make it the best use of it. What do you think where the clustered index is best used for?
Point query.
Point query? Point query, if you use it for point query, you have lost a big opportunity. For range query and order by queries, the clustered index is best. Why?
Because it needs to access a lot of pages.
Now, not only that, remember, if you have, let me give you the analogy. We all familiar with the catalog, the QU catalog that has the course descriptions. Yes. So the courses, if you look at the back of that catalog, usually the courses are listed. So if you want to find CS courses, they start with CMPS. So you do CMPS, let's say 101, okay? And then you basically jump into that page that have CMPS 101. And guess what? Where are the other courses, CMPS courses? Below. You just, once you land into the first one, all you need to do, close your eyes and keep reading, you find the rest. Yeah? If you want to, that is the power of range queries. Sorry, that is part of the clustered index. It's just a matter of landing in the first record that match your query, and then the subsequent records to answer the full query, where, let's say, for example, courses between CMPS 101 and CMPS 499, guess what? The rest are just next to you. Hopefully, you can find them all in one page. You read the first page, you get everything you want. If you finish the page and you didn't find CMPS 499, all you need to do is read the next page. And it's guaranteed it will have the rest of the information. Why is it guaranteed it will have the rest of the information?
Order.
Because actual data is stored.
Because the actual data is sorted based on the course code. Any of you seen the catalog, QU catalog? Yeah? So the courses are sorted by course code. So if you want to do a range query, this is the best. The clustered index is the best. Because all you need, you land into the first one, and the remaining ones are subsequent. And the database will be happy or not? Super happy. Remember, it tries to keep the related records that are more likely to be accessed contiguous. If we are using hard disk, do we need to move the ARM? Most likely not, because these blocks are contiguous. Yeah? If I want to say order by, get me the courses from CMPS 101 to CMPS 499, ordered by course code. It's already ordered. Yes, that is the power of clustered index. So don't waste clustered index, because most database, that is the problem. Most database, especially SQL that I'm familiar with, SQL Server I mean, when you create a table and put the primary key, by default, that graphical interface will create a clustered index on the primary key. Is it always the best choice? Definitely not the best choice. Yeah? Because most likely you will be doing point queries on that. It is helpful still, but not as helpful if you have some range queries. If you have some range queries that you're running frequently, you better put the clustered index on the columns that are frequently used in range queries or ordered by queries. Yes? So let me give you an example. Like if you take the transaction table in QNB Bank. Okay, so it has, for example, transaction ID, customer ID, account ID, amount, transaction date, and currency. You're all familiar, yes? The transaction table, can you imagine it? Yeah? So what do you think? Where should you put the clustered index? Can you repeat the schema? So you have the transactions, yes? Transaction has an ID. It has the account it belongs to. It has the date where the transaction was done. It has the amount. And it has maybe some labels, some description. And currency. That's it, six columns. Yeah. When you look up your, let's say, your transaction statement, that's what you see, yes? So what do you think? Which accounts you put in on account ID or date? Translate. Why we put it on date?
It's always ordered by date.
First of all, it's always ordered by date. And also when you go to your online banking, what they usually give you by default? The last, let's say, 30 days. Yeah. So you don't waste your clustered index on the account ID only. You might, even smarter way, you can do a composite index. What is a composite index? Two columns in one index. By customer ID and date, you put it as one index. Because most of the 90% of the queries will be querying transactions for particular customer between a page range. You follow it, yes? So that is basically what clustered index means. It's very important to keep this in mind. So let me go through this very quickly. Again, so in a clustered index, the actual data is sorted in the order dictated by the index. If you do clustered index on the transactions, on transaction date, on trans date, guess what? The actual table will be physically sorted based on the transaction date, which is good because when we go and query, when you get your, let's say, your bank statement, the transactions are sorted. They don't put them random, they are sorted. So that sorting is you get it free if you are doing clustered index. Okay. In a non-clustered index, the non-clustered index does not dictate how the data is sorted. The actual data is sorted. The other thing I mentioned, in a clustered index, the data and the index are one structure. In a clustered index, the index is separate. The index is one structure, and the data is another structure. And of course, the index points to the data files as pointers only. Yeah, that is the idea. So, but here you need to be careful because you have only one chance, one clustered index per table. You need to be careful where to put it. And here, this will help you to put it nicely. You put it on columns that you use for range queries, order by, group by queries. The clustered index is the best. And here, this is the power of the clustered index. If you are doing a range query, your challenge is just to find the first row in the range, and then subsequent rows are found following the physical order of the data. And by the way, when you are building a clustered index, typically using a B+Tree data structure, those pages are linked together. So you can traverse from one page to another. You can basically, they are linked. You can go from one page to another without going back to the tree to find the subsequent pages that are likely to have the records you are looking for. Just follow the links, the linked pages. Follow them. You will find your data there, nicely waiting for you and already sorted. That's what clustered index gives you. And I gave you the analogy of the QU catalog. All right. So this is just to illustrate this. It will become clearer as we move forward. Here is the clustered index. Take a look at this. And we will see this. This is a B+Tree. We'll see how this B+Tree gets built and how we query it. But this is how it looks like. It's like a tree, but it is in reverse, of course. You know, the tree, the roots are usually down and the leaves up. That's in the trees, in database, in the computer science, they are, the roots is up and the leaves down. Okay, so in a clustered index, guess what? What do we find in the leaves? The data itself. You can see here the index and the data, one structure. Look at the non-clustered index. We still have the tree, but what do we find in the leaf? Pointers to the data file, to the data pages. Pointers to data pages. That's another major difference between clustered index and non-clustered index. Okay. Another thing we need to understand in terms of indexing, there is something called sparse index. There's something called dense index. Sparse and dense. Yeah, sparse and dense. Okay, take a look at this. In a sparse index, this is my index entries. In the index, I have one entry per block. I have one entry per block. That's why it's called sparse. I don't have an entry per key. Look at those blocks. This is one block. This is another one, and so on. The first entry in the block is the one I have in as a value in the index. Yeah. So I don't need to store all the values. So for example, if I am looking for the people that start with B, there's no people start with B here. W. Okay, people that start with W. Basically, all I do, people that start with W, all I need to do, find the block that has W, and then forget about the index. Just follow the linked pages in the leaf nodes to answer my query. Because the data is sorted, I can afford to do this. If the data was not sorted, of course I cannot do this. Because in clustered index, the data is sorted based on the index. The data is sorted based on the index. So when we store, to be able to have a very slim index, we make it dense. What dense mean here? Like for each block, I have only one entry in the index. Yes? Now, what is the opposite of sparse index? No, sorry, this is the sparse index. I confused it. So the sparse index means I have one entry per block. Yes? Where I can use this kind of storage architecture of the index, I can only do it for clustered index. So for clustered index, another advantage of clustered index is the index, is it sparse or dense? Sparse. Is it something good or?
Good.
Why is it good? Why is sparse index is preferred?
We don't need to update the index on every entry.
That's very good. Like if we update, that's another good point. If we update any of the entries, we don't need to update the index. Okay, because the index only has the first entry. But more importantly also, the size of the index will be small. The size of the index is small because it is sparse. Now, compare that to a dense index. Here is a sparse index. Remember, here is a sparse index. So I have one entry per block. The first entry of each block make its way to the clustered index, to the sparse index. While here is a dense index. Dense index, let's say on age, every value of age, which is my index key, for every value, I have a value for each age and pointer where I can find the pages where I can find people having that age. So what we see here, this index we see here on the right side is a dense index. It has much more entries than the sparse index. Yeah. So the clustered index is a dense index, and the non-clustered index is I keep confusing them. The clustered index is a sparse index, and the non-clustered index is dense index. Okay, that's basically the concept. One more. This is very important also. A covering index. Any idea what a covering index is?
the query from the index from the full scan.
Sorry?
The query full scan from the index.
Yes, so basically when we can answer the query just from the index without going to the table, yeah, without going to the data files. I just want to jump here and just give you small examples just for you to put these concepts together in your mind, and then we move forward. So in here, what I have in here, I'll just go ahead and drop this table. Okay, so in here I'm creating this table here. It's not important, this first part. So I'm creating a table. This table has 3 columns: business entity ID, row with modified date. Okay, and then I go ahead and create. Can you see here? I'll go ahead and fill it and populate this table with some records. So I fill it here. There are 20,777 records added to this table. And then I ask the server, how many pages did you use to store this table? So the server can tell me. In SQL Server, there is something called management views. Some internal statistics and some internal data that the database maintains, you can ask it. You can ask the database to tell you some internal information. So in here, I'm telling it how many pages, is it all flat, or there is a layer, there's some kind of tree, or is it all pages without any hierarchy? So let me query it here. So you can see here, this 20,777 records are stored in how many pages? 96 pages. Okay, and the structure of this pages is a heap structure. Remember the heap structure we kind of discussed last time, where we basically have pages, and each page has slots, and we have slots, and we have the actual data. And the slots will have the record ID pointing to the offset where the data is actually stored. That's what a heap is. So we have 96 pages, and each page will have basically 2077 divided by 96. Okay. Now, take a look at this when I create a cluster index on this table. So the way I create a clustered index, all I do create clustered index, and this is the name of the index. You give it a name, and I say, please go ahead and create for me a clustered index on this table. The table is called demo business entity, and this is the column I want you to create the index on. So this is how I create the clustered index. Create clustered index, give it a name, and you say on which table and which column. If you have multiple columns, you can go ahead and add the multiple columns here. You can add as many columns as you wish. Okay, now once I run this clustered index will create a tree structure similar to what you see here. You create a tree structure similar to what you see here. Now, in the top part, you will find some index entries. Index entries. No data on the roots. We call this a root node, and these are called inner nodes. Inner nodes. Those nodes only store keys and pointers, keys and pointers. And on the leaf node, what we will find? The actual data. Yes? So as soon as I go ahead and create this, did I run it? Yes, I did already. Now, if I ask the database, how are you storing my table now? Because I created a clustered index. What do you think? How my table will be stored now? Is it still a heap? It is clustered index. So the data, where is it stored? In the leaf level of the clustered index. Okay, here, when I run this, it tells me, yes, your table now is stored. Your table now is stored on a clustered index. And by the way, this clustered index, how many levels it has? How many levels this table has now? One level. There's a root, and what's beneath the root? The leaves. And what we find in the leaves, we still have 96 pages that we had before. And then we have this root node of the index. This is very important node. This is the one I told you, remember when we discussed the buffer manager? When the database loads this root node, it flags it as high priority. Don't throw it away easily. Keep it there because it will help me query my table. I will show you shortly how we make use of this B+Tree index to speed up the query significantly. Significantly speed up the query. Okay, so far it's clear, the clustered index. Now, let me now show you a covering index. Okay, here is a how covering index looks like. All right, here it is. No, before I do that, sorry, let me create first another index. Remember here, I created this clustered index here on the business entity ID. And here I want to create a non-clustered index. By the way, if I try to do here, create clustered index. Sorry, let me first drop this index. I think I created this before, so let me just drop it. Does not exist, okay. Create. Clustered. Cannot create more than, it's already the IDE, this IDE I'm using already detected this. You cannot create multiple, okay? So let's not waste time on that and just put non-clustered. Now it's happy. Okay, run this. So it created another index. Now, this index, is it stored with the data or is it a separate data structure? It's a separate data structure. It is stored on its own set of pages, independent of the data file. Now, how is it linked to the data file?
Pointers.
By pointers. So some keys in this index will be pointing to pages on the data file. So now, if I go back here and ask again how my page how my table now is physically stored, it will tell me, oh, by the way, your table is stored as a clustered index, which means the leaf nodes will have your data. Plus, by the way, there is somebody created a non-clustered index, and that non-clustered index consumed how many pages? 40 pages. There's one page for the roots, and 39 pages for the leaves. What these leaves are storing, what we store in the leaf pages? Keys and pointers, keys and pointers. Yeah. So that's what we say. If they are occupying space, it's almost half space of the table just takes in the index. So if my database, if my table is 1 gigabyte, guess what? The index is 500 meg. Yeah, at least. Not only this, that's you say, oh, I don't care. And whenever you change this, you have to change this as well. Yeah, when you need to keep them in sync, otherwise this becomes useless. That is the idea of a non-clustered index. Okay, moving on. Now let me run. Yes, please.
The changes, you will do it as a developer, or it will be taken by the DMS?
As we discussed, the developer, they have more knowledge and visibility of the queries the application is using. So they are in a better position to suggest better indexes. Yeah, but also having said that, the BMS also have a lot of tools. There are a lot of tools out there that monitor the queries and monitor their performance. And there are even tools there. They call themselves index tuning wizards. Index tuning wizards. You just leave it watching your database for 1 day or a couple of hours or a couple of days. And then based on that, it analyzes those query results, these performance results, and it can suggest to you some indexes to put, yeah, based on the observations it makes. So it can come from developers as suggestions, or it can come from good DBAs that really care, then run their tools and do their job and get that. Without knowledge of the actual database, there are tools out there to help you do this. Yeah, most of them are commercial, expensive ones. They give you some trial version to run it for 15 minutes. Yeah, but there are tools that can help you do this. There are even tools that comes with, let's say, SQL Server. But those are like basic ones. There are commercial ones, much more powerful. Yeah. Yes, please.
Sparse, didn't you say that Sparse should, the clustered index is sparse?
The clustered index is sparse, yes. That's why, very good. That's another point. You know, the sparse index, physically, how many pages the indexes occupy? One page. Because remember, before we even created the clustered index, how many pages we had before when it was a heap file? 96. So the index, how many pages it's occupied? 1. Why occupied only 1? Because it is sparse. The other one, how many pages it occupied? Non-clustered, 40. Why is that? Because it is dense. It is dense index. For each key, it's maintaining pointer to the page where that key happens to appear. It took 40 pages to do that. So you can see here the difference. It will take a lot of effort to keep it in sync. And of course, it's taking some space. Okay, so let me now show you super quickly the covering index. Covering index. Yes, covering index, here it is. Yes, let me see. Here is a covering index. No, I need to drop this. Yeah. Okay, very good. Take a look at this. Take a look at this. Of course, this we will see later on when we cover query execution. But for now, what I'm doing here, I'm querying this product table where the name is cable lock. Yeah? Knowing that there is an index on this name. Okay, so what I'm doing here, I am querying based on the name, and then I am returning two things. I'm returning the product number and the name. The name will come from the index because I already indexed based on the name. But the product number, where the product number will come from? From the data file. So basically you can see here, to answer this query, I am doing two things. First, I do an index scan on the on this product name index. I do a seek, sorry, not a scan, a seek. I look up the index for the product where the product name is cable lock. This will give me what? One of the things it will give me is it will give me the pointer. It will give me a pointer to the data file that has the page that has information about this cable lock. Yeah, and then I'll do another lookup. I do a lookup for that particular page to retrieve all the information about that particular product. And then I'll get the name from this part of the query. I get this ID here. You can see the product number from this, and I merge them to get the results. Yes? So in here, to answer this query, I had no choice but to go to the data file because I'm asking for some extra information I don't have in the index. Now, if this query is very frequent, it will be nice to answer it just from the index. How to answer a query from the index? By creating what is known as a covering index. Take a look at this. So in here, I'm creating an index on 2 columns. What's the first column? Name. And I want the name to be sorted in ascending order, from small to big, in terms of alphabetically. And then what is the second column I'm creating the index on? The product number. So I'll go ahead and create this index, which is a composite index on 2 columns. Now, guess what? When I run this again, the query execution will be different. The database now will work out, oh, there is another index has been created. I will make use of it to speed up the execution. And take a look. When I run this and go to the execution plan, you see here, in one operation, I was able to answer the query. What was the operation? Index seek. I went to the index. Which index, by the way?
NonClustered.
This one. IX production product number name. You can see here. Here. The index what was used, can you see the name? IX product number.name. Yeah? So what do we call this type of indexes? Covering index. What does it mean by covering index?
Covers more than
No. Covering index means
You don't have to go to the data file.
I can answer the query just by looking at the index without going to the data file. Confusing enough? So basically, look, a covering index allows you to answer a query without going to the data file. So usually the normal way, especially for unclustered index, you do 2 steps. You look up the index to get the pointer to the page where the information is stored, and then you go to the data file and fetch that particular page to get the information, yes? And if you have a covering index, which has multiple columns, and those columns, you use them in the select. You can see here, what columns I'm using in the index? Name and part number. So the lucky queries that will ask for product number and name, we can answer such queries without going back to the data file. Why we can do this? Because the index has all this information. And what we, yes, please?
Sorry.
Yeah, and that's why this type of index, we call it a covering index. A covering index is an index that allows some queries to fully execute and get the answers just from the index without going to the data file.
Because the index has all the data. That's
Yes,
correct.
the index has all the data.
So if we add another column here in the select query, if we add another
Of course.
column, we'll go back to...
Yeah, of course, if you add another, even worse. Another message here, if you really don't always do star, because you are killing any opportunity for covering to use the covering index. Only get the columns that you really need, because you increase the opportunity if there is a covering index. Now or in the future, you can see this is the power of database. When you write your queries, they can run sluggish and very poorly. You put an index, somebody wakes up and put the right indexes, and everything stops. going so fast. But if you do star unnecessarily, you kill that opportunity. That covering index is just a waste. So if I do here star and I run here, we are back to square one. Yeah, 2 steps. Step 1, seek the index, get the pointer to the actual data block, and go and fetch that data block to answer the query.
So the covering index will depend on the query that you're running.
Yes, of course. This covering index, you need to carefully select those queries, those columns that you put in this covering index. You put those covering index for the queries that are heavily used, where you do that query together. Like for example, let me just give you an example. If you are, let's say, if you are in the back to the transaction, Q&B transaction. If I just want to give you the customer ID, the transaction date, and the amount, I can create a covering index. In this case, I will answer you super quick because I just go to the index and give you all the information. Sometimes there's something called include. Let me just, if I do here T-SQL, T-SQL is basically the SQL Server version of SQL. Every database uses SQL with their own spices, and so in SQL Server we call it T-SQL. In Oracle, I think they call it PLSQL or something like this. Okay, T-SQL, and I do here covering index with include columns. That's another way of doing it, with include columns. So you can either create a covering index. You can create a covering index like this, like the way I showed you, or you can create an index. Here I'm creating an index on postal code, and I'm asking the database, please somehow squeeze these extra columns in that index so I don't bother go to the data file. This is another way to do it. So you cannot search based on these. You cannot use them for search. But the information will be there in the index. So in one lookup, you get everything. So this is called covering index with include, another way of doing it. Yes. So but of course, if I do it this way, I cannot search by province ID or by city. If I search by city, it will not take advantage of the index. It will do full scan. It might do full table scan. But if I am looking by postcode, no problem. I can make it super fast to find information by postcode, and all other information will be there available for me from the index. So I save going back to the disk.
Does it have to be a non-clustered index for the covering index, or we can use also?
It can be for any. Okay. Yeah. So the covering index, it means the index include columns needed in the select part of the query.
What will happen if I put all the columns in the covering?
What will happen if I put all the columns in the covering?
Clustered.
No,
No point.
no, not really.
Performance.
Sorry?
There is no point of it.
There is point of it in the sense that, so basically you will speed up. You will do the answering in one. You don't put all. You put the ones that heavily used. But of course, the same problems. You will have a much bigger size index because the data is stored in there. And whenever you change any of those fields in the underlying table, you have to update the index. Yeah. So for example, index on postcode alone, it will only change if you change the postcode. But now, because you included these guys, whenever you touch the address and put a dot there or remove a space, guess what? The index needs to write text. So you are putting more. You remember the trade-off. The trade-off of the performance gain you get versus the computational cost of maintaining the index and the extra storage cost.
So I feel both the cover and the cluster index are very similar. Both are covering the data, and has the data on the index, and we can access the data, and we can specify some columns.
No, not really. No, big difference. Remember, the clustered index, the data is physically sorted based on the clustered index key. In here, it doesn't necessarily mean the data is sorted based on postcode. That's one. Second is this index is a separate data structure. It's separate. By the way, if I drop the clustered index, what will happen to the table? The table will be dropped. If you drop the clustered index, your table is gone because it is one thing. You get what I mean? So in here, this is not one thing. This is separate. This is separate data structure. And this is also what is it, dense or is it sparse? This is a dense index.
But it has like a copy from the data because
yes, it has basically copy of some of the columns of the underlying data. Yeah. So it has its advantages, but it's nothing compared to clustered index. Clustered index is a separate piece that help you with the range queries, with order by queries, with group by queries, and so on. The only advantage it gives you if your developers are careful and not putting select stars and they are retrieving particular columns, you can answer those particular queries just by looking at the index without going and doing the second step of retrieving the data page. Yeah, that's what it's giving. Okay. All right, moving on. Okay, here it is. That's the cover index. Okay, the last thing I want to just quickly introduce is now we get to the data structures. So as I told you, two major data structures that are used. The tree structure, typically the B+Tree, and the other structure is the hash table. Of course, there are hundreds of other data structures and algorithms related to indexing. So many, R-tree index, bitmap index, so many. Some of them are optimized for spatial temporal data, others for time series, others for geographic data with geolocations. So those are specialized data types with their own specialized indexes. Okay? And this is a research and development. There are PhDs and masters and companies working on this continuously. Yeah? Always people come up with much smarter way of doing indexing. But by far, these are the most commonly used one. The B+Tree index and the hash index. And other indexes, many of them are extensions of these base data structures. Okay. So here is, first of all, the motivation of full table scan versus an indexed access, just to visualize this. So in here, for example, if I want to search for, let's say I have a list of values and I want to search for the value 50. And suppose I don't have any index. So the only way I can find 50 is full scan. So I have to go through full scan. And if those values happen to be pages on disk, I have to bring every page. So the cost of this one is basically 49 record scan. Now, if I start doing an index access, such as a B-tree, this is how a B-tree looks like. So in here I have a root, and this root will guide me which path of the tree I will take to basically answer the query. So in here, if I'm looking for the value 50 and above, all I do, so in the tree there are three paths. The first path is values less than 30. This path is values between 30 and 50. And this path, values greater than or equal 50. Okay? So if I'm looking for values greater than or equal 50, close my eyes, I take the third path, and suddenly I ignored all of this. That's what B-tree allows me to do. This might not be very accurately done. Let me show you another example. Maybe it will be clearer. Okay. Maybe even this one. Let me show you full one. Yes, here it is. Here's a full one. Yep. Okay, here it is. Okay, this is a B+Tree, okay? If I'm looking for the value 22, this is the root node, these are the inner nodes, and these are the leaf nodes. If I'm looking for value 22, what do you think? Which blocks or which pages I will be visiting? So definitely I will need to look up the root. The root is the essential starting point where it will guide me which way to go. That's why the roots, as I explained, the database try to keep it in the buffer pool as long as it can. So I'll go to 17 and ask myself, is 22 greater than 17? Yes, so which path I will take, right or left? Right. So I'll go this path. And then once I arrive there, I'll say, now I'm faced with 27. 27, and I have 22, I'm looking for 22. So 22 is less than 27, so I'll take left path. And then basically I will land in the page I need. So to answer this query, what is the cost of this query? The cost is three pages. The first one, hopefully in 99% of cases, it's already cached in the buffer pool, which means to answer this query, how many pages I will need to read? 2. That is the power of the B+Tree. Yeah? In 2 reads, I am done. Yeah? Now, if I want to look for values greater than or equal 22, values greater than or equal 22, how I will answer this query? Same path. So greater than 22. So because I found 17 in the root, definitely it will be on the right. I take the right side, go through the right side. I find 27. 22 is less than 27, so I take the left side. I land in this bucket. I land in this page. And then once I land there, take a look at this. Take a look and be aware that the pages are linked. Can you see here there's a pointer linking the pages together? So all I do, I load this into the buffer. I will have the slots that having the row ID and the offset. I can even scan the whole page in the memory. That's not a big deal. Super fast. I scan, it's 8 kilobytes. Scan it quickly, find my 22, and then I'll go to the pointer, next page, retrieve those pages, next page, and so on. The last page will have a not pointer, which means that's it, no more pages. So the challenge here is just to land on the first page and look through subsequent pages next to the page I landed at. And because because the data is physically stored according to the order of the key, the pages will also be contiguous next to each other physically on disk, which make the reading super fast. There is no random access on disk. There is no movement of arm. We can pick up the data super quickly. So that's the idea of the B+Tree index. Let me show you here another example. If I'm looking for 16, so which path I will be taking? Left or right? Left. Yeah. So I'll take the left and land at the inner node, and then land at the inner node, and then I'll take the right. Yeah. And I will get that page, load it into the buffer, and then scan through it. Scan or do, even if when I load it in the buffer, I can do the, what is it called? The binary search. Remember binary search? If you have an array, and you want to do binary search, how do you do that?
Define two halves.
Yes, you go to the middle and ask yourself, is the value I'm looking for greater than this middle value or less than this middle value? If it is greater, I can ignore the first half and focus on the second half. And then go to the second half and again take the middle value and ask myself, is this middle value greater than the value I'm looking for or less than? If it is greater than, ignore the first half and just focus on the second half. And keep breaking that array into smaller chunks until you land on the value you're looking for. This can be done in memory super fast, and you can do binary search without full scan because the data is sorted. Binary search, you can only use it when the data is sorted. Yeah? And that's it. That's the idea of the... Now what is left is how this tree is constructed. How do we insert to the tree, how we delete from the tree. Yeah, that's what I'll be discussing, inshallah, next time. And also I'll be discussing the hash index, again, how it looks like, and how we insert into it, and how we delete from it, and how we look it up. Yeah. Now, this one is for range queries and for order by queries, and the hash index is for point queries. If you're looking for equality, you're looking for something by key, and you're using the equality operator, then the hash index is optimal. The cost is 0.1. Those of you still remembering complexity, looking up the hash index is a constant. It's super fast, but as long as you are doing point queries. If you are doing a range query, the hash index is useless. You have to scan the whole thing to answer range queries. So that's why, depending on which queries you will be using, you will need to choose the appropriate index data structure.